Opinions of residents in a town and surrounding area about a proposed racetrack is given here. This table gives the number of people who live in town and support the racetrack, who live in the area and oppose it, and those that live in the surrounding area that support and oppose it. A reporter randomly selects a person to interview from among these people. What is the probability that the person is for the track? So for the track means they support the track. So the first thing we want to do is total up the number of people who support the track. So if you add 3325 to 4747, you end up with 8,072. So there are 8,072 people surveyed, or that will, among the people that might be interviewed, who support the track. You're probably also going to want to know how many oppose it, so let's go ahead and total those. I'm sure we'll need it. And if you add those two numbers, you get 1,009. And we're probably going to need, I'm anticipating what we're going to need, you're probably going to need the grand total, which is just the sum of everybody. And if you add 8,072 to 1,009, you get 9,081. I'm sure we're going to need those individual numbers, so this is your grand total here. That's how many people are in the entire table. So what is the probability the person is for the track? Well, all you need to do is count the number of people for it, which is 8,072, and divide by the total number of people in the table, which is 9,081. I didn't write this down in the problem, but the instructions actually want us to give this answer as a reduced fraction, not as a decimal. So we need to be able to factor those reasonably large numbers. I noticed that 8,072 is even, so I know it'll divide by 2. It turns out it divides by 2, and when you divide by 2, the next biggest factor will divide by 2 again, so you'll get another factor of 2, and then the next biggest factor will divide by 2 again, and it leaves you with 1,009. And if you want to go off to the side and actually do that, I hope you've practiced some of this on your own. But if you took 8,072 and divided it by 2, you would get 4,036. And then if you divided that by 2 again, you'd get 2,018. And if you divided it by 2 again, you'd get 1,009. So that's how I got that. Same sort of scenario with the denominator. The denominator actually is not even, so it doesn't divide by 2. So you might try 3, and if you do, you'll find that it does divide by 3. And then the result divides by 3 again, and that 1,009 factor shows up yet again. Well, that's nice because you can just divide it out. So that really wasn't so bad. So the probability that a randomly selected person to interview from among all these people would support the track would be 2 times 2 times 2, which is 8, over 3 times 3, which would be 9. So the probability that a randomly selected person for an interview from this group of people would be for the track is 8/9. There's a second question The B part says, what are the odds against the person supporting the track? So what we need to do is remember that we already have a result from part A. We already know that the probability that a person would be for the track is 8/9. And now they're asking about odds. Whenever when I have a probability and someone asks me to change it to odds, I immediately break the denominator into pieces. Remember, probability is part to whole, and odds is part to part. So the part that I want is in the numerator, and the whole is the denominator when you're doing probability. So the part I want is 8. So if I take that 9 and break it into the part I want plus whatever it takes to get back up to 9, in this case is 1. 8 is what I want, and 1 is what I don't want. So when I break up and partition the denominator that way, I can immediately see what the odds are. So another thing, it says the odds against, but I think, as I said many times, I usually go ahead and calculate the odds in favor no matter what they want, and then I'll adjust it to make it odds against once that I've got the odds in favor. But anyway, back to the problem. The 8 represents what I want, and the 1 represents what I don't want. So when you're doing odds in favor, you're going to get 8/1. It's just that simple. If you take the denominator after you've partitioned it, you've got the odds staring you in the face, but it's the odds in favor. They actually ask for the odds against. But once you have the odds in favor, the odds against would be 1/8. You just simply switch them. Okay, let's continue. Brand new problem. If a dart is thrown and hits somewhere in the diagram, what is the probability that it hits the shaded area? Now, the probability, if it hits in that area drawn, the probability it hits in the shaded area is just simply proportional to the area of the shaded area versus the area of the whole thing. So the first thing we have to do is find the area of the shaded area. We've got to find that shaded area. Here's what I probably would do. If you look at it this way, the shaded area is this. Actually, the shaded area is not all of this, but let's just say for the time being we're looking at that. If I'm trying to find the area that I've just shaded in there, that's easy because it's just a 4x2 rectangle. And the area of a rectangle is length times width. So I would get 4 times 2. for the area. But remember, that's too much. I'm including some things that don't belong in there. I don't want this part included. The white area, I don't want that included. So let me just clear all of this. I need to get rid of, this 8 represents too much area. I need to get rid of everything except the shaded area. So I need to take out this much from the 8. 8's too big by that much. But that's a 2 by 1 rectangle. And that's 2. So what I've done now is I've found the area of the bigger rectangle, 4 by 2, and then I've taken out the 2 that I really don't want. So I end up with the shaded area being 6 square inches. Okay, once I found the area of the shaded area, I need to compare that to the area of the entire thing. We're going back to the way it looked in the beginning. The area of the entire dartboard, funny looking dartboard, but nevertheless, that's what they're saying it is 8 by 4. So the entire dartboard area is 8 by 4, which is 32. So by the basic probability principle, the probability that the dart hits the shaded area I don't know why it's doing that. It's just, well, I don't know why it's doing that, but let's just let it do it. I'll write it over here. The probability that the dart hits the shaded area is simply the ratio of the shaded area to the total area. That's 6 over 32. And of course, this time I didn't write this up here, but they want the answer written as a decimal. And they want it to 4 decimal places. So this time you don't need to worry about reducing. You have to pay attention to the instructions. They want it written to 4 decimal places. So it's 0.01875. Excuse me, 5. And part of the lesson you're learning, I hope, by watching these is you have to pay attention to the instructions. So the previous problem wanted it reduced as a fraction. This problem wanted it written as a decimal to 4 decimal places. You have to pay attention to what they're asking you to do with the final answer. Let's do one more. Okay, this problem says cystic fibrosis is an inherited lung disorder. Because the gene for cystic fibrosis is recessive, 2 apparently healthy adults who are called carriers can have a child with cystic fibrosis. We will use N for a normal gene and C for the recessive cystic fibrosis gene. So they're using a capital letter for the normal gene, and they're using a small c for carrier, and the small c indicates that it's recessive. Now, whether you've studied this in biology or not, all they're really asking you to do is cross-reference these things. If you've got a small c with the small c, you end up with CC. If you have a small c with a capital N, you end up with a CN. If you have a N with a small c, you end up with capital NC. And if you have a N with an N, you end up with NN. Now, it says that a carrier has one normal gene and one of those recessive genes. So you can look through here and you can see that this would be a carrier, and this would be a carrier. The double N's would be normal, and the double C's would be an indication that the person has the disease, has cystic fibrosis. Okay? So let's go to the second part. The second part is, what is the probability that the child will have cystic fibrosis? Remember, I'm not going to sketch in the whole table, but what we ended up with from the table was CC, and that means the person would have the disease. We had CN, which meant the person was a carrier. We had NC, which meant carrier, and we had NN, which meant normal. Now these are equally likely, so the probability that the child would have cystic fibrosis would simply be, you'd count every one of the four where the child would have cystic fibrosis and divide by the total number of possibilities. So whether you know a lot of biology or not, or have done this before, it's basically just a labeling and counting problem. So the probability that the child would have cystic fibrosis, if you're looking through there, there's exactly one where the child would have cystic fibrosis over a total of 4 possibilities: the CC, the CN, the NC, the NN. So the probability that the child would have cystic fibrosis is 1/4.